In this video, we are going to learn what a Maclaurin series is. In our last video, we saw some examples of what Taylor series were. So we had this Taylor series for e to the x. This one happened to be centered at x equals 0. And that's why all these terms are just like x squared or x to the third, rather than like x and then minus some other number to that power. We also did an example where it wasn't just centered at 0. That was this natural log one centered at x equals 1. That's why all these coefficients were in front of like x minus 1 to some power. So we had looked at some of these Taylor series examples. And what a Maclaurin series is, it's a special Taylor series for a function when it's centered at x equals 0. And the formula for these coefficients is really similar to the one with Taylor series. In general, a sub n, this coefficient, involves doing the nth derivative of the original function and plugging it in at the center point 0, divided by n factorial. So there are several common Maclaurin series, and I think it's helpful to just kind of list all of them together. So if I have 1 plus x squared plus x cubed, so on, this is a special type of series. We've seen it before. This is geometric. This is geometric. Because to get from one term to the next, I keep multiplying by x. So I multiply that by x, multiply this by x. So that's that common ratio. And we've seen before that, hey, a geometric series converges as long as this common ratio, its absolute value, is less than 1. And when that happens, the sum, the formula for it is it's a over 1 minus r, where a is the first term, and then r is this common ratio. So if I use that sum formula, I get an expression for what this equals. So a for this is 1 over 1 minus the common ratio is x. And what that means is this 1 plus x squared plus so on, that whole thing just equals 1 over 1 minus x. That's a simple formula for what this whole expansion is. And that works as long as absolute value of x is less than 1. All right, so next up, e to the x, it's Maclaurin series. We've seen this one before in the last video. Let's put this in sigma notation. So I know on the numerator, I get all these powers of x. So I'm going to write x to the n. And on the denominator, I know I have a factorial. And that number getting factorial matches the exponent. So if my exponent's an n here, I need an n factorial on the bottom. So after I get my sigma notation, it's helpful to plug in the first couple of values for n and see if it matches what I have. So if I plug in 0 for n, I get x to the 0 over 0 factorial. But x to the 0 is just 1. 0 factorial is 1. And that's my first term. That's the 1. If I plug in 1, I get x to the 1 over 1 factorial. But that's exactly this. So that's checking out. For cosine x, this is the Maclaurin series, it turns out. So I just have these even powers of x, factorials on the bottom, and then I alternate pluses and minuses. Sine is really similar, except you just have these odd powers of x. And again, there's this alternator. One thing to check is, hey, the derivative of sine is cosine. I'd encourage you to check that if you did the derivative of all of these things, this polynomial, you'll get the cosine Maclaurin series. So let's write these in sigma notation. I actually want to first have you practice this. So give the video a pause for maybe 2 minutes to try putting those in sigma notation. In 3, 2, 1, pause it and try that. Okay, let's talk about it. So for cosine, on the numerator, I have these x to an even power, which I can denote with x to the 2n. And then on the bottom, I have a factorial that matches like that exponent. So I'm going to write 2n getting factorialed. And we've seen before that an alternator is created by something like negative 1 to the n, or maybe negative 1 to the n plus 1. To check if this is right, let's plug in the first couple values. If I plug in n equals 0, negative 1 to the 0 is positive, and that checks out with this number. X to the 0, that's just 1. 0 factorial is just 1. So that is giving me this first term. If I plugged in n equals 1 into this, I'd get a negative, and that's making sense with the next term. For sine, to get these odd powers, I would need x to the 2n plus 1, right? Because these powers are 1 more than they were for the cosine term. And then the same thing, factorial on the bottom, 2n plus 1 factorial. And then the same alternator, negative 1 to the n. So it turns out for e to the x, cosine x, and sine x, they equal these Maclaurin series for all x. Any x value that I plug in to both sides, they're going to be exactly equal. But for this first one, there's just a limited domain of x values where they're actually equal to each other. So there's a few cool results we can get from this. So like if I know what the x values are where this works, I can plug in one of those x values. So in the second equation, if I were to plug in, let's say x equals 1, on the left-hand side, I just get e to the 1, which is e. On the right-hand side, I will get this, sum of the reciprocals of the factorial. So somehow weirdly, this whole thing just equals e. Okay, there's one thing I want to be careful about when I plug in. If I take this first formula, and if I were to now try plugging in x equals 2, which I'll put in a different color, what I would get is this. But now something kind of weird happens. This left-hand side just simplifies to -1. The right-hand side, you keep adding bigger and bigger positive numbers, so that's going to be infinity. But -1 is not equal to infinity. So even in the previous step, these are not equal. So why did this not work? Whereas for this previous one, it did work. I want to have you think about that for a quick, let's say 30 seconds. So pause it in 3, 2, 1 to think about, why does it not work when I plug this in? Okay, let's talk about it. So the reason it doesn't work is the only allowable x values for this Maclaurin series is when absolute value of x is less than 1. And 2 doesn't fit that description. It's not in that acceptable interval. So the problem with this is, hey, this geometric series converges when the absolute value of x is less than 1. That's why I wasn't able to plug in something like 2. And finally, a key fact. A Taylor series equals the original function on some interval around x equals a. So this is most clear to see, I think, in this first example. If I were to represent on a number line what absolute value of x is less than 1 is saying is, well, the center point of this Maclaurin series is 0. And when absolute value of x is less than 1, that means I'm in between -1 and +1. So any x value in this interval, when I plug it in, it makes both sides be equal. For all these other ones, they work for all values of x, which means they would work for anything in the whole number line. So my interval is infinitely long.